Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 12.5. In this video, we're going to deal with trickier piecewise sums. Okay, so let's go ahead and get started with the first example. So you already know immediately these are all in terms of floor functions. If you remember from the previous video, whenever we see a bunch of floor functions and only floor functions, this is, this is obviously not an integral. I mean, it's an integral, but in competition terms, this is just a sum problem. So we go ahead and turn this into a sum immediately. Infinity. Our lower bound is 2, so we start n equals to 2. ln of n squared minus 1 over n squared. Alright, now what? You see, this is like one of the most annoying things that I hate about integration, piecewise integration specifically, is because, we're not here to solve sums. We're here to solve integrals. But here, we're given a sum. So this is the most annoying part. So how do we solve this? What do we do? What on earth do we do? So whenever you stumble upon a sum like this and you don't know where to go, the best thing to do, the first strategy, is to construct it. Or I wouldn't say construct it. Express it in terms of an actual sum. And what I mean by that is we'll go ahead, well, actually, because it's inside of an ln, summing up an ln means that this is a pi product, technically. Okay. So let me first start off with that. And then this is n squared minus 1 over n squared. Okay. So it's a pi product because it's ln. Okay. But where do we go from here? So go ahead and express it in each term. And this is going to help us see what is going on. So let's go ahead and test that. Plug in 2. We can actually, let me go ahead and turn this. We'll turn this in terms of n minus 1, n plus 1. Okay? And you'll see why. So 2, plug in 2, we get what? 1 times 2 plus 3. Okay? Then we get 2 times 2. I'm going to turn it like this. And then because it is a pi product, alright, and then n equals to 3, we get 2, 4, 3 times 3. Okay. And then 4, 3 times 5, 4 times 4, etc. 5 times 5 here, and then it would be what? It would be, let's see, 4 times 6, right? Again, I don't know what's going on, right? I don't know what I'm doing, but there's a pattern here. This cancels out, okay. This cancels out. This cancels out. This cancels out. This cancels out. This cancels out, and then it keeps on going and going and going forever, infinitely. Oh, huh. Interesting. So what this means is that this sum, it telescopes. And so, because of that, this integral and the sum equals to ln of 1/2. Okay? So whenever you see some kind of a weird function, express it, go ahead and express it in sums or in products, but that's only because whenever you have an ln, you just turn it into a pi product. But whenever you have a weird sum, go ahead and express it, evaluate it in terms or in expressions. So another example is if I had something I don't know, some cosine of pi nx whatever, right? You go ahead and, this looks weird. I don't know what to do with this sum. So you go ahead and express it and see what's going on. And then, okay, n equals to 1. That's like, oh, I don't know why I put x there. But like cosine pi n. Okay, times 1, that's going to be negative 1 over 1. If n equals 2, it will be a plus. Oh, n equals to 3, it would be negative back. Oh, wait a minute, I know this sum. This is a Taylor series for ln of 2. Oh, I think this one's a negative? I think it's like x ln, right? This is pretty much this, in a way. Not exactly. I don't think so. Oh, this should be n. Sorry. Is there a negative? Oh, there is a negative, plus 1. See if I plug in 1. Oh, no. Okay. Yeah. So this would be this, I believe. So yeah. So again, like I said, if you're given something weird, express it in terms, and then see if something looks familiar to you. Okay? Don't let it intimidate you. Alright, just immediately turn it into a sum. Okay. N equal to 1 to infinity. And n plus 1. We have 2x of x minus n minus x minus n square, x square, n square dx. Okay. Interesting. Let's factor this. I'm just going to put a sum there for now. So we can factor this, x minus n, 2x minus x minus n. Okay. This is equal to x plus n. Interesting. So this is equal to so x square minus n square, x square n square dx. Okay, so what we have here is we have 1 over n square. I'm just going to put that at the back. And simplifying this, we have 1 minus n square over x square dx. So that's literally what we're having. Oh, well, actually, let me combine the 1 over n square. This is what we're having. This is what's going on. So what we have is 1 over n square minus 1 over x square. Yeah, that's what we're having. Okay. Cool. Again, we can simply integrate this. This is no problem. So when you simply integrate this, let's see, this is just 1 over n square. And then here, integrating this, we get 1 over x. So this is what? This would be like plus 1 over n plus 1 minus 1 over n. Okay. And so now, it's, this is straightforward. This is a Gauss sum, pi squared over 6, plus there's a telescoping series, plus 1. I'm sorry, wait. Ooh, wait a minute. N plus 1. 1. Oh, I'm sorry, this is minus 1. Ooh, be very careful. Be extremely careful. I had to plug in my, I had to plug in terms, and it's minus 1. And then the rest cancels out on this side. So pi squared over 6 minus 1 is our answer. Okay? Be very careful. So, yeah. Not too bad. Not too bad. So we have this integral here. Again, you know what to do with composite functions. Now, you can't do this manually because the reason why we can't do this manually, you'll realize, okay, if I try, doing this manually, let's see, from 0 to 1, oh, well, we're already from 0 to 1. So when you let u equal 1 over x, then you realize, wait a minute, this becomes 1 to infinity. Ah, so because of that, it actually does, this is technically a piecewise integral where summation is needed. Okay? So, from 1 to infinity, we go ahead and turn this to a sum. N equals to 1 to infinity. We have n to n plus 1, x minus n over x cubed. We'll just turn it back to x, just cause. Okay. So now what? We just simplify it. Go ahead and simplify it further. I don't blame you though. Variable constants can be just a little bit annoying, but that's okay. Okay. So that's what we have. So now this is when we integrate that. This is what? This is negative 1 over x. So actually, I'll go gentle. We'll start with this because this side's going to be positive. Let's say that's going to be like n 2x squared minus 1x, and then from n to n plus 1. So n equals to 1. N plus 1, we plug in n plus 1, we get n plus 1 squared here, minus 1 over n plus 1, and then plug in n, this is what? 1 over, oh shoot, I'm sorry, ooh, be careful, wait, we are subtracting, this is n squared 1 over 2n, minus 1 over n. Okay. And then if we simplify this, you can see that we end up with n to n plus 1 squared minus n plus 1 plus 1 over n minus 1 over 2n. And then 1 over n minus 1 over 2n. Do I want to combine that? I don't know if I want to combine that. Do I want to combine? I guess I'll combine it. So this would leave off as plus 1 over 2n, because 1 minus 1/2 is 1/2. What on earth do we do with the sum? So now with rational functions, I'm going to be honest with you, it's not pretty. But luckily, this is a lucky case. A lot of integration B problems tend to be this pretty, actually. And what I mean by that is it's just simple partial fractions most of the times that you'll be dealing with. So in this case, what we have here, we can actually simplify this by doing plus 1 minus 1, right? So start small things and then kind of build your way up, and you'll start your ideas will start expanding. So we have 2 n plus 1 here minus, we have this, which we don't mind leaving out because it's a Gauss sum. And then look at this. N plus 1, n plus 1. So what we have is 1 over 2n minus, right, if we combine this and this together, it turns to be 1 over 2 n plus 1, right, because a half minus 1 is negative 1/2. And then we have the negative, and then 2n plus 1 squared. Okay? Here we already know this is a telescoping sum, so this is equal to 1/2. Okay? and then minus 1/2 of, let's see, this is pi square over 6. However, if you plug in n equals to 1, we started with 2. So this is technically pi square over 6 minus, and because we're missing that first term, so it would be 1 here, minus 1. Yeah. And so now our answer, our full answer, is 1 minus, let's see, oh yeah, because negative 1 distribute, yeah. So 1 minus pi square over 12. This is our answer. Okay? So again, whenever you have a sum with rational functions, try partial fractions. Okay? Or like algebraic manipulation like this. Pretty much how you would deal with rational functions in integrals. Okay? So we have this factorial one, but we still have an x squared at the top. So let's go ahead and turn this into a sum. Well, technically we just have this. 1 over n factorial, n plus 1, x squared dx. So of course we already know this is going to equal to, well, just looking at this, we're going to have like 3n factorial, and then n plus 1 cube minus n cube, right? Which this is technically equal to 3n squared plus 3n plus 1, 3n factorial. So what we have is we're left off with this sum, n squared n factorial plus n factorial plus 1 over 3n factorial. Okay, so how do we deal with this? I'm just going to have this as 1/3 e, so e over 3, plus, and then n equal to 0, we have, this is, I'll simplify this first because that's n minus 1 factorial. Wait a minute. N minus 1 wait a minute, something's wrong. N minus 1, if I plug in 0, I get negative 1 factorial. Oh no. Okay, so we stumbled across something bad. We'll keep these together. Okay, while we have plus 1 over, or technically, what? E over 3? E over 3. Okay. Because this portion here is the easiest. Right. So we just have to do with this. Let's see, plug in 0. We know this is going to be 1. Plug in 0, it's just 0. Oh, I think that's what it is. I believe we find out what went wrong, right? We canceled out n, but if n equals to 0, I don't think we just cancel it out like that, right? So be very careful. So what that means is this n equal 0 is useless. So we just go back to and change it into 1. Okay. So we have n plus 1. We technically have n plus 1 over n minus 1 factorial. But here I can go minus 1 plus 1. Because we have n minus 1, we can, n minus 1, we plug in 1, it's 0. So now that's useless. N equals to 2. We can shift it. And now we can go ahead and use, n minus 1 over n minus 1 factorial, right? That cancels out. So now this is 1 over n minus 2 factorial. Okay? So this, this is another dangerous case to be careful with when you're dealing with trickier sums. Okay. So we have e equals to 3 plus 2 of, let's see, plug in 1. Oh, this is technically still e, right? Because it's like n equals to 0 for 1 over n factorial. Here, same thing, e. Okay, so we have e of 3 plus 1/3. This is equal to 10/3. So our answer is 10e over 3. Okay, so be very careful. We nearly died there, right? There was something wrong, like, well, we can't plug in this and that. So whenever you realize that if your first term equals to 0, you're gonna have to shift it. If you're gonna do some manipulation, check if the initial term is 0. If it is, shift your initial term, and then you can go ahead and continue. Otherwise, you're gonna end up with some awkward, unusual fallacies. Okay, so that was actually a good demonstration for that. So just be aware, be very careful. We're this close to getting a little Romanian style here. I wouldn't say this is a Romanian style integral. I guess, kind of, ish, a little bit, just a little bit, but not exactly. Or I guess this could be like a beginner Romanian style piecewise integral. But pretty much, it's not too bad. Let u equal 1 over x, right? Let u equal 1 over x. This becomes 1 to infinity. We know this is going to be 1 over u with the u square at the bottom, so u cube from the du. And then we have a ceiling u and a fractional part u. Okay. So this is what we have. Now let's go ahead and turn this into a sum very quickly. N equal to 1 from n to n plus 1. N plus 1, x minus n. Turn it back to n. I'm sorry, turn it back to x. Okay. We rewrite this. The most annoying part. Okay. So we could technically take out the n plus 1. So we could take out the n plus 1. That's just a constant. Here, what we're dealing with is the x. See, we have 1 over x squared minus n x cubed. Okay. So now what we have, to put n plus 1 here. Now what we have is we have minus 1 over x. This is going to be n 2x squared from n to n plus 1. This looks familiar, doesn't it? Huh. This looks so familiar. Okay, so we have n plus 1. We have n 2n plus 1 square. Huh, interesting. This really does look familiar. Okay, and then minus 1 over 2n plus 1 over n. Huh, this looks completely familiar. This looks completely familiar, doesn't it? It really should, because I feel like we did this sum before. Well, not exactly, but this parentheses part, the parentheses portion. But it's okay, we can do it again, right? Practice. So, again, we're given some weird, well, actually, we could technically shove this in, right? So, first off, I like to simplify this. This is plus 1 over 2n now. And when we do plus 1 minus 1, we end up getting, I'm just going to speed integrate this, or speed sum this. We have 2n plus 1, but we have a minus 1 here, so this is negative 1/2, technically, minus this, and then plus 1 over 2n. Okay. But now we have n plus 1 that we have to distribute. Okay, so now what we have is n plus 1 over 2n. Okay, and then we have minus 1/2, and then we have minus 2n plus 1. Okay. Because this is infinity to n equals to 1, this looks divergent, right? You probably say to yourself, this looks divergent. We have a half here. I don't know what this is. What do we do? Right. Well, thankfully, if you split this up, right, this half cancels out with this half. So we end up with, oh, would you look at that? Everything cancels out so nicely. 1 over 2n minus 1 over 2n plus 1. A telescoping sum. So our answer is just simply 1/2, because we can just factor out the half. Okay, cool, we're done. All right, so again, another practice, don't be intimidated by these sums. Start small, especially with rational functions like this. This scares a lot of people. I don't blame you. It'll make me hesitate too, but just start doing partial fractions or some algebraic manipulation like this. Okay? Ooh, interesting. Let's go ahead and let's force u sub that. Right. Let u equal square root of x. We get back 1 to infinity, 2u, and then this floor function on top here, du. Interesting. Interesting. Let's go ahead and sum that up. Right. N equals to 1 to infinity. That's simply a half n at n plus 1. Then we're stuck with 2u du. Huh. Okay. So this is u squared. So what we have is this sum, 1/2, and then we have u squared with n plus 1 square minus n squared. And this is equal to 2n plus 1. Yeah. So what we have is 2n plus half n, technically. Okay? I'm going to just put a bracket here. Okay. So what do we do here? This is technically, I don't know why I wrote it like this. I think it would be better to just have it like this. Don't you think? Technically? Sum. Okay. But the point is, how do we compute this? So, I mean, this side is easy because that's geometric series, right? Okay, no biggie. Okay, so we know how to compute that right side. Let me rewrite this again. This is n equals to 1, what was it? 2n plus 1 to the power of n. So how do we compute this? Right, so we know the geometric series. This is what, 1, oh well, n equals to 1, so be careful. So it would be a half, 1 minus a half. So this would equal, I'm sorry, I'm just speed summing this. 1, so we have 1 plus 2 of the sum, infinite sum of n over 2n. How do we compute this part? There's two ways, calculus and algebra. If you remember the intermediate training of how to compute something like this, right? I demonstrated how you would solve it by hand. Just to recap how to solve this, you let s equal, and you have to explicitly turn it into the sum to 2 square 3 2 cube, right? And then you kind of multiply by 2s, 1, this is 2, this is 3, 2 square, and then you do 2s minus s, 2s minus s is equal to s. And what this does is it gives me this minus this minus that, gives me plus 1, right? I'm sorry, no, 1/2, sorry. This minus that gives me 1/2 square, and then it becomes a geometric series. And this equals to like 1/1 minus half, this is equal to 2. So, and that's why this sum here is equal to 2. Times 2 plus 1, you get 5. Okay? Another intimidating looking integral again. Don't be intimidated, just go straight to summation. Just go straight into summation. Alright, so with the sum, we have, this is, let's see, anything, I think this is this part that we can take out. -1 n plus 1. And then from n to n plus 1, everything else we do have an x minus n to the power of n here. We have 2 to the power of n technically here. So I guess we could take that outside. 2 to the power of n. And then we have x minus n here. Okay. dx. Again, this becomes n minus 1. And this is okay because we can let u equal x minus n. And this gives us a cleaner integral. Right? If we have n plus 1 to n and n plus 1, then we have u minus n minus u to the power of n minus 1 du. So we have, I'm just going to put a sum here. Quickly write this. This is pretty much u to the power of n over n, right? U to the power of n over n. Oh, I'm sorry. I forgot to put in the bounds. 0 to 1. I was like, this doesn't seem right. N to the power of n. But no, it's the bound is from 0 to 1. Okay, cool. So this is 1 over n. So what we have, infinity, an infinite sum of -1 n plus 1 of n to the power of n. Okay. So another way is to use calculus, like which I also mentioned in the intermediate series from the infinite function video. Right, let x equal 1/2, because that's technically what we have. So what we have here is like n plus 1 x to the power of n or n. This is ln of x plus 1. Okay, so our answer, so it seems that because this is a Taylor series, this is equal to ln of 1 plus 1/2. So our answer is equal to the ln of 3/2. Cool. Alright, next integral. Okay, this is our last integral. And I want to throw this one at you because there is an identity that you should definitely be aware of. It's actually not common. Kind of rarely shows up, depending on where you're from. But we have an identity called Wallis Product. And this is an example of one of those integrals that has this identity. So let's go ahead and just simply turn it into a sum so that you know what am I talking about. N equals to 1 and n plus 1, and we have a -1n x dx. This is simply, we already know what this is. From -1, we have ln of n plus 1 over n. Okay? Again, you're probably thinking, what the heck is this? What is this sum? Right. So we express it Well, technically this is ln of pi of n equal to 1, right? Because it's inside of ln. But then we have n plus 1. If we kind of express it, plug in 1, right? Okay, but we have a negative here, so I don't know why I have this pi product here. This should go away because we're expressing it. But we end up with this. And you're going to get this. 5, 6, 6, 7, etc. And you're probably thinking, I've never seen this before. And that is okay. That is normal. It is normal for you to not know this identity. Okay, if you do, then you are either a math Olympiad or some mathematician that has already gone to the void. So, let me go ahead and erase this top. So what on earth is this product? This is Wallis product. Let me show you what that is. Let me write this in orange, or I'll write this in purple to be royally fancy. So, Wallis product states that when you have a pi product of n equals to 1 and it's 4n squared minus 1, or you can rewrite this as 2n, and then this is 2n minus 1, 2n plus 1. So in other words, when you have something like this, it starts with 2 over 1. And then it goes 2. So it starts 1 time, and then starts 2 times, and then it goes like this. Okay, it starts 1 at the bottom, and then 2 times on top. Okay, 1 once, 2 times on top. Okay, and then it goes like this on forever. This is equal to pi over 2. Okay, this Wallis product identity, this is equal to pi over 2. Therefore, the one that we have, the integral that we have, is equal to ln of 2 over pi, because ours is flipped. Okay, so our answer is ln of 2 over pi. Okay, so I just want to throw that out because you will see that very rarely, but I mean, I just want to make sure, depending on what country you're from, you know, if you're from United Kingdom or Australia or some other country that does high-level integration, you might stumble across this identity, this Wallis product. Okay? Alright, that's about it for this section here. So I hope that was helpful. Again, rewatch this video and try the integrals yourself so that you become more comfortable solving these piecewise integration problems, especially with summations. Okay? Alright. Thank you so much for watching, and I'll see you guys in the next video. See ya.